Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we're examining aldehydes and ketones, specifically the reactions that aldehydes and ketones undergo. We're continuing our investigation of reaction chemistry of aldehydes and ketones, examining reactions with hydrogen cyanide, or HCN. If an aldehyde is reacted with HCN in dilute base, molecules referred to as cyanohydrins will form. A cyanohydrin is a molecule in which the C double bond O has become an OH, and a cyanide is attached on the same carbon as the OH group. This molecule is referred to as a cyanohydrin. Cyanohydrin. Now the base is utilized since HCN is such a poor nucleophile. Deprotonation of HCN yields, if you deprotonate HCN with hydroxide, you will produce the strong nucleophile cyanide. Now only a small amount of base is used because as the cyanide attacks the aldehyde, cyanide is now a strong nucleophile. If it attacks the carbonyl, you produce a base, an alkoxide. And the base that forms can further deprotonate HCN, liberating more nucleophile. So the base can now react with more HCN, and that will liberate more cyanide to go back and react with more aldehyde and generate our cyanohydrin. And this goes back over here. Now, this deprotonation of HCN occurs because the O- group is extremely basic. In terms of chemistry, cyanohydrins are interesting in of themselves. However, it is the products that can be formed from the cyanohydrin that are especially important. Cyanohydrins can further be reacted either into α-hydroxycarboxylic acids, or they can be reacted to form β-aminoalcohols. Okay, let's take a look at both these types of reactions. Let's start with α-hydroxycarboxylic acids. So, alpha-hydroxycarboxylic acids. How does this reaction work? Essentially, all that's involved is taking the cyanohydrin and reacting it with H3O+. Sometimes heat is added. And the cyanide group becomes a carboxylic acid. And hence, the carboxylic acid functional group is here, so this is the alpha carbon. The alpha carbon bears a hydroxy group, hence the term α-hydroxycarboxylic acid. Now, the mechanism for the actual hydrolysis process is rather drawn out and looks fairly long if you examine it in your notes. It can look intimidating. But if you examine it closely, you will see that all that is happening is the gaining and removal of protons and also the addition of water molecules and loss of amine. So let's begin with the mechanism, and we'll start with the original cyanohydrin and see how we can get to our final product here. Now, going down, we're going to add H plus and protonate the nitrogen, which you should note has a lone pair of electrons right there. And of course, if you went back, it's minus H plus. And so our first step, I'm going to draw it over here, try to maximize the use of my room. Is the protonation of the nitrogen. Now that increases the electronegative characteristics of nitrogen. Also, I can draw a resonance structure where 2 electrons move out onto the nitrogen. If I do this, I get a C double bond NH with a lone pair now, and my carbon is positively charged. Now that is susceptible to attack by water. Note, if you have H3O plus around, you're dissolved in water. Water is a weak nucleophile which will attack carbocations. If it adds, I get CH3, CH, OH, C, O. There's my water molecule that added. There's a lone pair there. And the double bond is here. And as you can imagine, we lose a proton off of the OH. Minus H plus. So you see all that we're doing is adding water and putting on protons and taking off protons. That's all so far. Nothing that difficult. The hard part will be remembering. Better give a little more room. The hard part will be remembering. So we get an OH here, double bond, N, H. The hard part will be remembering where these protons actually go. Now we're going to add H+. Now if I added H+ to the OH again, it would just get me back to the same thing. If I added H+ to the other OH, it doesn't really get me anywhere, but I'm going to protonate the lone pair on nitrogen. And that'll give me an H plus double bond C OH and there you go. Okay, of course this is in resonance. With the structure. Remember there's lone pairs here. I'm going to move that H over here. And here. So if I dump this lone pair in and that lone pair over here, I would get this guy. NH2 with the lone pair. C double bond O H positive. CH Okay, and what's interesting is I could draw a resonance contributor here where these electrons didn't move down and I have a carbocation. Now what's interesting is if this middle resonance contributor deprotonated, if we pulled a proton off of that, we'd get this structure. Move that positive over here, put it up there. And we pull the proton off. Now this molecule right here is an amide functional group. So incomplete hydrolysis or partial hydrolysis takes you through to the amide. But this structure certainly can be attacked now. By water. If we add water, we'll get a positive charge there. We'll still have our NH2. We now can deprotonate. Minus H plus. Give me a CH3 CHOH. A lot of OHs on this molecule now. COH, NH2, OH. And now we're going to, okay, so going back would be plus H plus here. And of course this was plus H2O, so there would be a minus H2O going back. So now, if we add a proton to the nitrogen, we could turn the NH2 group into a fairly decent leaving group, an NH3+. We have a COH, OH, NH3+. Okay, getting a little crowded here. Now, I'm going to take this and then I'll show what happens last step. I'm running out of room. I'll take this down this far. Minus NH3+. Now the NH3+, when it leaves, it becomes NH3. The NH3 very quickly, in mild base, will grab a proton and go to NH4+, because NH3, ammonia, is a very powerful base. So this guy will become NH4 positive. Now, once you lose the NH3, you have this carbocation. Actually, let's move it over. We have our OH, and then we have a C with two OHs and a positive charge, a carbocation. Well, that certainly does not look like my carboxylic acid, but in actual fact, if you look closely at it, you can see that it is. Let's zoom in on that molecule and take a closer look. So we have a CH3, a CH with an OH, and two OHs. With a positive charge. Well, note those two OHs have lone pairs. All the oxygens that are OH have two lone pairs. And I can draw resonance contributors where I dump in one lone pair towards the positive charge. If I do this, I get a protonated carboxylic acid. Likewise, I could have dumped in the lone pair from the other oxygen. If I did that, I would get this resonance contributor. Now, protonated carboxylic acids are very acidic. Carboxylic acids that have an extra proton readily want to lose that proton. So all of these structures, these resonance contributors, will lose an H+. And in fact, this reaction at the stage, I'll take a closer look at that, at the loss, I may have used equilibrium arrows, and that may have been inappropriate. We'll go back and look at that in a second. But when you lose a proton here, what you finish up with is this molecule. An α-hydroxycarboxylic acid. Okay, now let's ask one question. The point at which we formed this, the point where this resonance structure was formed by the loss of, remember, minus NH3. I used equilibrium arrows, and we really should ask the question. And so you remember it came from this guy. Would it be proper to use equilibrium arrows on this step where the NH3 got kicked out? So remember, we had an OH, an OH, and we had protonated the NH2 and made an NH3+, which is a reasonable leaving group. NH3 is ammonia and is a base when it's kicked out. Could NH3 come back in on this resonance structure and generate an equilibrium? What would NH3 do to this resonance structure? Well, as I said, this resonance structure is extremely acidic. If NH3 came in and attacked, it simply would deprotonate. NH3 would not attack as a nucleophile, adding to the C+. Rather, NH3 would just come in, grab a proton, and give you NH4+. So if you look at the reaction in the reaction mechanism in your notes, you'll see there are equilibrium arrows throughout the whole structure, equilibrium and resonance arrows throughout the whole reaction mechanism, until you get to the NH3 step, which is a single arrow because there is no equilibrium, because the NH3 will grab a proton and become NH4+. That proton may come from solvent, or it may come from the protonated carboxylic acid, this resonance structure up here. If he grabs a proton off here, this minus H+, right here, that minus H+, will go on the NH3, making NH4+. Because of that, there's no lone pair on nitrogen for it to go back. It can't attack this electrophilic carbon. It can't nucleophilically attack this carbon. Net result is the loss of NH3 is an irreversible step, whereas the other steps of the reaction are all with equilibrium error. So that's not a mistake. That's very important to understand. Okay, so that's the synthesis or the reaction mechanism for the formation of an α-hydroxy carboxylic acid. All right. Now, why don't we take a look at the formation of the other species that can form from cyanohydrins, and that is the β-aminoalcohol, formation of the β-aminoalcohol. Now, beta-aminoalcohols can react, beta-aminoalcohols can be formed by reaction of a cyanohydrin with lithium aluminumhydride, powerful reducing agent, and in a completely second step, subsequent hydrolysis with water. And this will produce Now, the alcohol is the highest priority group, and it's located off this carbon. So the alcohol functional group is attached to this carbon, which is the alpha carbon. So your functional group is the alcohol. This is the alpha carbon, so these are beta carbons. The amine is attached to a beta carbon, hence the term β-aminoalcohol. How does this reaction proceed? Well, the reaction mechanism is not as complicated. Essentially, step one adds H minuses, which are attached to the carbon because the carbon is delta plus. You see the nitrogen's electronegative. And because of that, there is a delta plus on carbon and a delta minus on nitrogen. And when the aluminum hydride approaches, there's a delta minus on its hydrogen and a delta plus on the aluminum. Essentially what happens is the hydride attacks the carbon, pi electrons move towards the nitrogen, and the nitrogen dumps electrons to aluminum. Now this is much easier to see if I draw a minor resonance contributor for the cyanohydrin, since the nitrogen's electronegative. This would be, although minor contributor, an important contributor. Okay, and so we now have a full plus on the carbon and a minus on the nitrogen. And so if I again draw my aluminum hydride, delta minus, delta plus, it's not hard to see that the hydrogen would go here and the negative charge would attach to aluminum, and you would get CH3, CH, OH. And you'd have a C with an H and a double bond now with a nitrogen lone pair and an aluminum with 3 H's off of it. So the aluminum interacts with the nitrogen, helping stabilize it. If the process happened again, and we could go through the same full process with lithium aluminum hydride, effectively you can do the same thing, add a second hydrogen to that carbon, and the charge on the nitrogen would be stabilized by the aluminum atoms. So lithium aluminum hydride puts the hydrogens on carbon, and you'd have aluminums with or without the hydrides stabilizing the nitrogen. The final addition of water hydrolyzes the aluminum, breaking it down into aluminum oxide salts, water-soluble salts, and protonates nitrogen, giving you your final β-aminoalcohol. So the two H's, these two H's right here, they came from the lithium aluminum hydride. They came from LiAlH4. But the two hydrogens that go on the NH2, they came from the water. Now why not use acid? If you had used H3O plus here, because amine's a base, you would protonate it and you would have formed NH3 plus. We don't want the ammonium salt, so we use water. That way it stays an NH2 group, or you will be able to isolate significant amounts of NH2. To guarantee that you have it as the NH2, you might even at this point throw in some hydroxide as well. The problem with presence of hydroxide is it might precipitate out the aluminum salts. So you have to be careful. You want to keep the aluminum salts water soluble and separate the amine. But you certainly could add a small amount of hydroxide to make sure no protonation of the nitrogen actually occurs. Alright, so as I stated, cyanohydrins can be converted to alpha-hydroxy amino acids, alpha-hydroxycarboxylic acids. Did I say amino acids? I meant alpha-hydroxycarboxylic acids and beta-aminoalcohols. Well, big deal. What's so important about that? Well, you may recall earlier this year I did a little talk about anesthetics. One of the local anesthetics used in dentistry is this molecule. Now, you don't have to know this molecule. I'm not going to test you on it as part of this course, but this is an interesting point. So we've got a C double bond O, a CH2, and we've got an N. We've got a CH2CH3, CH2CH3. And it's often written as HCl, which basically means there's an H attached to its nitrogen, which makes it positive, and a Cl minus. But it's often written as the amine HCl, or the hydrochloride. This material, right, is referred to as lidocaine and is a local anesthetic used in dentistry offices. But all these local anesthetics have a side effect, an undesirable side effect. They can cause a drop in heart rate and blood pressure. And to compensate for this, a molecule known as epinephrine is added in trace amounts. So they actually inject adrenaline with the lidocaine to increase the action of the heart and compensate for the drop in blood pressure. The structure of adrenaline is this structure. And I want you to look closely at this structure, keeping in mind what we've just covered about alpha-hydroxycarboxylic acids and beta-aminoalcohols. Here's the structure of epinephrine. And lo and behold, look at this. Here's the carbon, which has my OH group. That's my alpha carbon. Here's a beta carbon. And what do we have off the beta carbon? We have a nitrogen. This is a beta amino alcohol. Adrenaline is a common biomolecule. It's used in dentistry offices in local anesthetics. It's a very important molecule, and it's a beta-amino alcohol. Synthesis of such molecules is important. And so having easy access via cyanohydrins to beta-amino alcohols can be useful in synthesis of such biomolecules. This represents just one example. Okay. Well, let's move on now and take a look at the reaction of ammonia and amines with aldehyde. Having looked at the reaction of cyanide, what happens if I react ammonia? Well, if I react ammonia with aldehyde, I am required to use a very narrow pH window. For ammonia, that window's around pH 3 to 4. For other amines, it'll be around pH 4 to 5. We're going to talk about that in a second. Now, if I do this, I will produce an imine. Now, in common nomenclature, this aldehyde is referred to as acetaldehyde. The resultant imine is named exactly the same as the derivative aldehyde, acetaldehyde, imine. But the word imine is added after it. And when I see imine, I know to replace the double bond O of the aldehyde with the double bond NH. The problem with acetaldehyde imine is that it's unstable. And imines with hydrogen off of the nitrogen readily polymerize. Start linking together, producing long chains. More commonly, we take an aldehyde, such as, say, benzaldehyde, and we react it not with ammonia, but rather with an amine. For example, we might use CH3NH2. In such a reaction, we use a pH window of about 4 to 5. In order to understand the function of such pH windows, we will need to look at the reaction mechanism, and we will shortly. The result is the replacement of the oxygen in the C double bond O with a C double bond N, and we still have the CH3 off. The CH3 helps prevent the polymerization. If this molecule is benzaldehyde, what you see here must be benzaldehyde imine, because the C double bond end is an imine. But you'll notice if I say just benzaldehyde imine, there is no distinguishing. Okay? If I just say benzaldehyde imine, there's no distinguishing between an NCH3 and an NH. So imine's insufficient. In actual fact, this is a benzaldehyde methylamine. So in front of imine, we put the name of the alkyl group. Benzaldehyde methylamine. You should be able to name, using common nomenclature, all of our imines and methylamines. If this was an ethyl, it would be an ethylamine. If there was a phenyl off the nitrogen, it would be a phenylamine. Well, as I said, why do we have to have this narrow pH window? Well, to do this, we have to examine the reaction mechanism. So let's take a look at that. I'm going to start with an R. R could be my phenyl group. RC double bond OH. And I'm going to react it with methylamine. CH3NH2. And if I react that, I get RCO. And I get my lone pairs around the O. That's O minus. In fact, you can't see that lone pair. I'm going to move this all down a bit. Just down a little. There's an H on that carbon. And we've added an N. This N, of course, it's an NH2, so it has two H's off of it. And there's the methyl. All right. Next, I'm going to lose an H+. Certainly, this group can leave. Going back would be minus CH3NH2. I'm going to minus H+, lose acid from the nitrogen, giving me RCH. We now have NH, lone pair, CH3. And then we're going to add H+ and protonate the O-. Plus H+, RCOH, NH, forgot my H. Forgot the H here. Okay. This looks like the NHCH3 group of the that we saw earlier in the molecule epinephrine. Okay, so what next? Well, I can protonate again. I certainly could add a proton to the OH to make H2O+, which is a very good leaving group. And so I could produce RCH OH H. Get the good leaving group water. And we have NHCH3. Lone pair here. If water leaves, so going back would be minus H+. Going back up here would be minus H+. And going backwards here would have been plus H+. Okay, so now I have this RCH. I lose my water. I get RCH+, and I have attached to that NHCH3. Okay, and we lose water, so obviously going backwards would be the addition of water. Okay, so I've lost water. Now I can draw a resonance contributor where I dump in those two electrons from the nitrogen, and I make an RCH double bond N, and we have a H and a CH3. And the positive charge is now on nitrogen. This is referred to as an iminium ion. The iminium ion readily loses a proton. The iminium ion readily loses a proton and gives me my imine. Now you notice in water, because you have to add water, and acid, that this would be reversible. So methylamine would convert back to the aldehyde if we threw it in acid, lots of water. But in base, like methylamine, we can drive the reaction through to the imine. But there's a narrow pH window. Why the pH 4 to 5? Well, let's consider an extremely basic pH. Let's just use pure base, pure methylamine. So a pH up around 10, 11. What would happen? Well, the nucleophilic attack certainly would happen. But then we'd have a problem. Okay, and the alkoxide might pull a proton off of here. That'd be okay. But look at the stages where we have to add H+. This stage, for example. To get the good leaving group, right, we have to, well, possibly pull the H+. That might happen, okay, if base didn't grab it first. It might get on the alkoxide. You might get to this. But then you got to add another H+ to make the good leaving group water, right here. At high pHs, this would not happen. There would be no H+ available. So high pHs, this step won't happen. So if you're very basic, this step won't happen. Because you have to add protons. Okay, well, let's go acidic. Let's make it very acidic. Let's throw in lots of acid. Won't we protonate the OH, kick out water, and then easily kick off a proton? Yes, but think of the nucleophile. CH3NH2 is a base. If you throw in lots of water, the lone pair will protonate. And if you protonate the CH3NH2, and you get CH3NH3+, there's no lone pair in the nitrogen for it to act as nucleophile. So for this first step, right, at low pHs, this won't happen. So at low pHs, this won't happen. So pH 4 to 5 is required. pH 4 to 5 is required to allow optimal conditions of not too low a pH and not too high a pH, so that you have enough concentration of the free lone pair in nitrogen to get appreciable nucleophilic attack, and you still have enough protons to protonate the hydroxyl group and kick out water. Alright, so the pH window is very important. Now, imine chemistry was very important. We looked at imine chemistry in the transamination reaction of amino acids, and I'm not going to draw that reaction again, except to say that imine chemistry is very important biochemistry, and the transamination reaction by which most living organisms convert one amino acid into another is absolutely important, and you can take a look at that by turning back in your notes to amino acid chemistry. Now, I want to leave this mechanism up because it is very similar to what would happen if we used a secondary amine. Now, I'm going to draw the reaction summary on the bottom. You notice that what we've done in this reaction to produce the imine is that we attacked it with a primary amine. That is a methylamine. A secondary amine, what would happen if I used R? Okay. Well, let's actually make the R group a methyl. Let's use CH3, C double bond O, CH3. Let's use acetone this time. Throw in a ketone. And instead of methylamine, let's use dimethylamine, a secondary amine. Dimethylamine. Again, we're going to keep our pH window of 4 to 5. Do we get an imine? And the answer is no. We get what looks like this. We get this type of molecule. So if we take acetone and we react acetone with dimethylamine of pH 4 to 5, we will get, what have we got? We've got a propane, we've got a propene, so we have two methyls of nitrogen. It looks like we've got an N dimethyl prop 1-ene 2-amine. What have we formed? What kind of functional group? Well, we've got an ene and amine. We formed something that's called an enamine. Enamines form in reactions with carbonyls and aldehydes and ketones, pH 4 to 5, and secondary alcohols. Why don't we get an imine? Well, let's take a look at one very, very important feature. And that is this H. If I follow this H all through the imine mechanism, we can see that that H is crucial to the formation of the imine. It is the red H that is the final H plus that is lost in our mechanism. Now, if I change my methylamine, so instead I don't have CH3NH2, but rather I have CH3 twice NH, then this red group is no longer an H, it becomes a CH3. The mechanism for Enamine formation is exactly the same. All the way down until you get to here. When you get to here, the loss of H plus can't happen off of nitrogen. You can't pull an H plus off of nitrogen. So what happens? You have a carbocation here. Right? This step minus H plus won't happen. So let's take a look at what does happen. Well, what would happen is if this guy were CH3, you'd still minus the H plus, but you'd pull it off of the CH3. So this guy would lose his H, make it a CH2H. The H plus comes off here, and these would form a double bond. And you'd get a CH2 double bond. This would stay a single bond. and you'd have your CH3 here. You'd get your enamine. In other words, you do an elimination to make a double bond. Now, if I go back, all the way back to the imine, and I go back to just one, CH3 and H2, well, why didn't we form an enamine when we had a primary amine? Why not pull the H off the carbon? Why pull the H off the nitrogen here and form the imine? Why not pull it off the CH3? Well, when an H is on nitrogen, the protonated iminium sp squared hydrogen on sp squared orbital attached to nitrogen, because nitrogen is so electronegative, it wants to hang on to those electrons. This proton's more acidic than that of an sp cubed carbon. So you pull off this H first, and you get an imine. But when there is no H to pull off that position, you'll pull the H off of here and generate the enamine. So what's interesting here is enamine mechanisms and imine mechanisms are exactly the same, right up to the very last step. What changes is only the last proton you pull off. So look carefully at those two mechanisms, and when you look in your notes and you see a mechanism for imine formation, a mechanism for enamine formation, you're actually learning the same mechanism. And you should understand why enamines form in contrast to imines. And you should be able to explain the difference. But you're really learning only one mechanism, and there's a change in the last step. And in fact, you're pulling a proton off in the last step. The only change is where the proton comes. If it comes from nitrogen, it forms an imine. And if you have a choice, it will come off the nitrogen. But when this is a CH3, you can't pull an H off the nitrogen. There is no H on nitrogen, so you pull it off the carbon. And you form the enamine. Okay? You still get an aluminium ion, by the way, as part of the resonance structure. So why don't we clear that up? With the whole mechanism drawn here, it may be a bit confusing. So why don't we draw this out again? So we've got a CH3. We've got a CH. And then we have an NH, CH3, positive on carbon, and a lone pair. So we got to this point in our reaction mechanism. Now, in the case of the aldehyde, we could draw a resonance contributor. Let's draw it this way. To the iminium ion. And I'm going to change the H to an R group. So we're looking at the very last step of our reaction mechanism. And we have these resonance structures. Now what's interesting is the next reaction is minus H+. That happens in both enamine formation and imine formation. But when R equals H, you form an imine. That should be a plus here. When R does not equal H, for example, it equals methyl, you form an enamine. Now look at this carefully. This is just showing the last step of the reaction mechanism we had up previously. If this R is an H, it can be pulled off as H+, and you'll get the imine, because you'll just pull off the H+ here. However, if this R is not an H, it can't be pulled off as H+. There's no H+ off nitrogen to pull off, and so what you do is you pull an H off here, and that moves the two bonding electrons between here to make the double bond. Right. The last thing we want to look at in terms of imine formation is the reverse of the imine reaction, the hydrolysis of the imine. As I pointed out, imines, the imine reaction mechanism was reversible. It was totally related by equilibrium errors. I said if you threw in water and acid, the imine would go backwards. And all it is the previous reaction drawn in reverse. If I had, for example, the ketone, okay, here's a very good thing. How do you name something like this? I mean, you see a molecule like this, what do? When you see a C double bond N, replace the NHCH3 with an O and name it. Well, that's obviously acetone. And then just add in, so you replace whatever's there with an O, add in your NCH3, and you know a C double bond ends imine, name the alkyl group, and so this is acetone methylimine. There you go. Now if you take acetone methylimine, we can go through our protonation step. And I'm just doing the reverse of what we did previously. But I think it's worth drawing out again, just so you see it, and hopefully you're practicing this along with me. You're actually taking the time to do this. I encourage you to do that when you look at these scribble casts. And of course, there's a resonance structure. Move the pi electrons towards the positive charge. And what does that give me? That gives me a positive on the carbon, making it susceptible to nucleophilic attack. So now we can add water. Water comes in and acts as a nucleophile. And we can lose a proton. If you look carefully at the previous mechanism, you will notice that this is just the formation of an imine going backwards. We now can protonate the nitrogen to make a good leaving group. If we do that, so there we go. Now in acid, this step is not reversible. Under normal circumstances, but if you have that narrow pH 4 to 5 window, it would be reversible. And we discussed that in that narrow window, NH2 can react. You probably wouldn't be using that if you want to drive the reaction to completion, but because it's possible, I'm going to draw it as an equilibrium arrow. Okay, you'll kick out, in this case, NH2CH3. Which it would go on and get protonated if you used very acidic conditions, and the reaction would not be reversible. What we get here then, of course, I'm going to draw this differently now. It's this guy. It's carbocation, which I can resonance stabilize with this. And very quickly lose proton. Giving me my ketone. Now I want you to look closely at this. Start from the ketone. Nope, plus H plus would protonate, giving you your resonance structures. This was minus NH2CH3, so on this side it would be plus NH2CH3. Aha! You'd get that, then you'd have minus H plus going this way, plus H plus. Then over here, going up, we'd have minus H2O. Once that happened, you have your resonance structure, get the iminium ion, and then here you'd have minus H plus. And you have the mechanism between acetone and acetone methylamine. So, which mechanism you draw here really depends on whether you're given the imine and asked to hydrolyze it to make acetone, or whether you're given acetone and you asked to react it with amine under pH 4 to 5 conditions to make imine. In your notes, you see both mechanisms given to you, but they're really the same mechanism. Now, the hydrolysis mechanism is important because there are molecules out there where you don't want hydrolysis. One of the problems with imines is that they are so easily hydrolyzed. And the reason for that easy hydrolysis has to do with the availability of the first step in the imine of this lone pair to protonation. You see, the first step is protonating that lone pair. If that couldn't happen, this process would slow down and the molecule would be more stable. How can we make this lone pair here less available for protonation? Well, that can be done by replacing the CH3 group attached to nitrogen with a more electronegative atom. If we replace the CH3 with, say, an NH2, nitrogen's more electronegative. What does that do to this lone pair? The greater electronegativity produces more positive charge on the nitrogen with the double bond in the lone pair, effectively causing the orbital to shrink somewhat. The electrons are held more tightly, more closely, and less available for protonation. It's as if the electronegativity of this nitrogen is increased. It stabilizes lone pair that's less available at protonation. This first step is less likely to happen. As a result, molecules that replace in imine type structures, C double bond N structures, carbons offer them with more electronegative atoms, are more stable. The concentration of the resultant iminium ion, this guy, is so low for these species, and the reaction is so slow that effectively the hydrolysis does not occur. Well, we're going to look at that in our next Scribblecast, and we're going to examine the types of molecules that will help stabilize the C double bond N unit. I'm Dr. Brian Lloyd. This is my Scribblecast. Thank you very much.